Uh, Welcome to our video for section 5.2, where we are going to talk about the limits and continuity of vector functions. So we'll start off with the definition, and this is definition 5.2.1 in the textbook. Let R be a three-dimensional vector function defined on an open interval containing the real number a. So the open interval contains the real number a. Um, and we have got a possibility that the function might not be defined at a. Now, if c is a vector in R3, then the limit as t tends to a of RT is equal to c if the following is true. And the following says, for every epsilon, there exists a real number delta greater than 0. So for every epsilon greater than 0, there exists a real number delta greater than 0, so that um, the absolute value of t minus a is between 0 and delta, implies that the norm of r of t minus c is less than epsilon. Right, so we are going to uh, get into a theorem right away. Theorem 5.2.2, and it says, let R be a three-dimensional function with components x, y, and z, defined on an open interval containing the real number a, except possibly at a. Now, if C, the vector C, which is C1, C2, C3, there's supposed to be a bracket there, is a vector in R3, then the limit as t tends to a of r of t is equal to the vector C, if and only if the limit as t tends to a of x of t is equal to c1, limit of as t tends to a of y of t is equal to c2, and the limit as t tends to a of z of t is equal to c3. Right, and we're going to look at an example to illustrate uh, the application of the theorem that we have. So consider the vector function r of t, which is t, first component is t squared, the natural log of the absolute value of t, and then the second component t squared minus 1, where t is not equal to 0. So we show that r of the limit as t tends to 0 of r of t exists, and we want to find the limit, the value of the limit. So we can see that the function is defined except for the value t not equal to 0. So which is well, so it basically satisfies this definition, because we said except possibly at the point a. So in this case, the a is equal to 0. Right, so let's look at the solution. So the components of r are x of t is equal to, so the first component x of t is equal to t squared natural log of the absolute value of t, and then y of t, which is equal to t squared minus 1, and we need our condition that t is not equal to 0, otherwise x of t will not be defined. So clearly the limit as t tends to 0 of y of t exists. This is a simple calculation, and we just say limit as t tends to 0 of y of t becomes minus 1, because we just put our 0 there, and then we get it, the value, right? So it therefore remains to show that the limit as t of 0 of x of t exists, and we have to find its value. So note that x of t can be written, so it's t squared natural log of the absolute value of t can be written as a fraction, the natural log of the absolute value of t, over and then if we put that down at the bottom at the denominator as a denominator, t squared becomes 1 over t to the minus 2. And since we know that the limit of the limit of the natural log of the absolute value of t uh, as t tends to 0 goes to minus infinity, and from and if we look at the denominator, the limit of the denominator, so as t tends to 0 of t to the minus 2, we know that that is going to plus infinity. It means that we are able to apply L'Hospital's rule. And what does it say? It says that we can then differentiate the two functions, right? The numerator and the denominator. So for the numerator, we get 1 over t, and then for the denominator we get minus t cubed, I think, and then so if we divide, we then end up with okay, so this one was, if we differentiate, we get minus 2 times um, so it's minus 2 times t to the minus 3, which in the end gives us something like that. And so if we take the limit as t tends to 0 of that, we get 0, right? So by the L'Hospital's rule, the limit as t tends to 0 of x of t exists, and it is equal to 0, as we have shown there. Therefore, by theorem 5.2.2, the limit of r of t exists, and the limit of r of t as t tends to 0 becomes, the first component will be 0, the second component limit will be minus 1, so we get that vector 0, minus 1. Right. So once we have that, then we can look at rules for addition of limits, for scalar multiplication of limits, and all that that is involved in that. Right. So let R and W be three-dimensional vector functions defined on an open interval containing the real number a, except possibly at a. And then assume that the limit as t tends to a of r of t is equal to c, and the limit as t tends to a of w of t is equal to d. Then the following statements are true. So we'll see that the first one tells us that if we add the limits of the limits of the limit of the sum of the functions is equal to the sum of the limits, right? So so it says that it exists, and the value is c plus d. And then if we do a scalar multiplication, then the limit of the scalar multiplication is just the scalar multiplication times the limit, right? That is number 2. Then number 3 tells us about the dot product um, uh, of of limits. So if the limit or if we take the limit of the dot product, we get the dot product of the limits, right? And then if we have the cross product, then the same is true. And then if f is a real valued function defined on an open interval containing the real number a, except possibly at a, and we are told that the limit as t tends to a of f of t is equal to L, then that means that the limit of the product of the function f of t multiplied by the vector r of t exists, and the limit is just L times the limit of the vector function. And so those are the properties that we have on vector functions. We are just extending these from what we already know uh, about functions, or about vectors rather. Right, and then the theorems. The theorem is the proof is left as an exercise. You can find it exercise 5.2 number 2. So go and look at that. But basically all of them follow from 5.2.2, and then the rules that we already know about uh, vector addition, scalar multiplication of a vector, cross product, dot product, all that. Right. Let's go on to another definition. Definition 5.2.5 in the textbook. Let R be a three-dimensional vector function defined on an open interval containing the real number a. Then R is continuous at a if the limit of R of t as t tends to a is equal to R of a. And again, these are things that we already know from continuity. It's just now it's component wise. So theorem 5.2.6 tells us what I've just said. So let R be a three-dimensional vector function defined on an open interval containing the real number a with component functions x, y, and z. Then R is continuous at a if and only if x, y, and z are continuous at a. And again, the proof follows from 3.5 sorry, the proof follows from theorem 5.2.2, and it is an exercise in the textbook, exercise 5.2 number 3. So you can go and check it out and do the proof. Um, Lastly, we will have a definition just to wrap things up. So a curve C in R3 is the range of a continuous three-dimensional vector function R from I, where I is an interval in R, and the R maps to R3. So what does that mean? That means that C is just R of t, where t is from the interval, and the function of R is called a parameterization of the curve C. Right, so that is all for 5.2. Go and check out the proofs and do the proofs to satisfy yourself. You're using what you already know, and that's all you need in this section. So do the proofs and do the exercises. Thank you.